Hey, so I was cast for season 41 of Survivor, so I'm gonna be gone for a while. And I need someone to watch over Zuzu's tank. Would you be able to do that?
What? Sorry, Elsa. I have to prepare for this Harry Potter trivia night.
Would you be able to take care of Zuzu while I'm gone?
I don't know, I have a really important wine competition. It's super competitive.
Okay. Will you be able to take care of Zuzu while I'm gone?
Sorry, Elsa. I'm preparing for a baking contest.
What am I gonna do?
Every day, college students like Elsa are faced with this difficult decision: to leave their reptile unattended throughout the day to cram for their exams, or attempt to study in their loud and cluttered apartment. That's why Team Chef de la Gartixa, made up of 3 of the brightest engineers at NC State, Kyra Sigler, Joseph Ishak, and Kaylee Saarinen, have come up with a device to ease some of the daily stress a typical college student and reptile owner carries. The group of students spent hours researching the necessary information, such as leopard gecko care, the appropriate temperature conditions, the best heating lamps on the market, and various automatic heat sensors. And what they came up with will help little leopard geckos like Zuzu all across the nation. We'd like to introduce to you the first ever temperature-controlled heating lamp that can almost send a notification to the owner in the case of an emergency.
After performing preliminary research, the team came together to assemble this set of project objectives. First, to identify a temperature sensor to be used in a habitat with a temperature range from 75 degrees Fahrenheit to 100 degrees Fahrenheit. Next, to identify a circuit component to be used as a switch for a heating lamp. Next, to design a control system using the identified components in an Arduino Uno. After that, we would develop a circuit schematic to illustrate the physical components of the system, as well as develop a sketch in Arduino IDE to output an on or off signal to a heating lamp in response to an input signal representative of the habitat temperature. If that was able to be accomplished, we would like to identify compatible shields to enable wireless or remote communication by the Arduino Uno system, and develop a sketch in Arduino IDE to enable wireless or remote communication by the system when a threshold temperature signal is exceeded.
This diagram shows the original setup we had in mind. We will talk about the different components and we will discuss the changes made due to the missing parts. The temperature in Zuzu's tank must remain between 80 to 90 Fahrenheit. There are many sensors that would work adequately within this range, but we found that the DHT11 sensor is best for this setup, mainly because it contains a chip that does analog to digital conversion, providing the user with temperature in the form of a digital signal. This would make it easy to implement it in any microprocessor. All is needed is a 5-volt power source, a ground, and a signal wire going to the Arduino. The DHT11 sensor is capable of monitoring the temperature and the humidity of the surrounding environment. If the user decides to enable the humidity feature, we included a couple of hidden lines in our code as comments that can be activated as desired. The Wi-Fi module we intended to use in our original setup is the ESP8266. Combined with the Blink interface, it would allow us to monitor and control the temperature of the tank remotely. We were able to acquire the Wi-Fi module, but we couldn't get it to work properly. The ESP8266 require a stable 3.3 volt power source averaging 100 milliamps. Unfortunately, we didn't have a secondary power source for the module, and the Arduino is only capable of providing a maximum output of 40 milliamps. Therefore, we decided to remove the module and have an LED bulb to visually monitor the setup. To display the temperature, we used a 16:2 serial LCD screen. Usually those screens require a total of 12 connections, but to make the setup simpler, we decided to combine it with the I2C bus. This reduces the number of connections to 4, power, ground, and 2 analog connections with the contrast potentiometer mounted on the back of it. Another component we initially had in our setup is the 5-volt trigger relay module. The relay makes it possible for the Arduino to control high voltage devices without causing any damage to the board. The intention was to use it to control the heat bulb, but unfortunately we weren't able to acquire neither the bulb nor the relay, so we decided to use a white LED bulb to represent the signal sent by the Arduino to the relay, as we will demonstrate in the simulation. Finally, the Arduino Uno RV3. It's a low-cost open-source prototyping board capable of receiving digital and analog inputs, processing them in its microprocessor, and providing desirable outputs. The Arduino Uno has 14 digital inputs, outputs, I/O pins, and 6 analog input pins. In addition, modules and shields can be connected to it, adding more features as desired. In our case, it will receive the signal from the temperature sensor, processes it, and based on the results, it provides the desirable output using the LEDs and the LCD modules. From the components discussed previously, we were able to build a setup to monitor and control the temperature, as we will demonstrate in the following slides.
Okay, so now we have about a 3-minute video of our simulation, so sit back and relax and I will narrate what is happening. So first we have a temperature input of 114 degrees Fahrenheit, which is above our set temperature range of 80 to 90 degrees Fahrenheit. This causes the green and the red LED to turn on. The way our system works, the green LED is on as long as the temperature is above the minimum value set. For us, that's 80 degrees Fahrenheit. Once the temperature exceeds the maximum, the red light also turns on to indicate that the temperature is above range. Now we see the temperature drops to 89 degrees Fahrenheit, which is just below the max temperature that we set for our range. This causes the red LED to turn off, leaving only the green LED on and indicating that the temperature is in range. Here at 80 degrees Fahrenheit, we see that the red LED comes on again. This is because the red and green LED combo also indicates an error, and at this point, Joseph had to unplug our temperature sensor in an attempt to get it to cool down quickly. Ideally, this scenario would have led to a notification being sent to the owner of the sensor. But as Joseph explained in his section, we were not able to accomplish the remote notification part of our design. You can see that once he plugs the temperature sensor back in, the red LED turns off. Now the temperature drops to 79 degrees Fahrenheit, which is just below the minimum value that we set for our temperature range. You can see that the green LED turns off and the red LED turns on, indicating our temperature is below range, and the white LED turns on, which represents our heating lamp, meaning that in this scenario, the heating lamp would be turned on. Lastly, Joseph unplugged the temperature sensor one last time to demonstrate the error mechanism. You see that the white LED shuts off and the red and green LED both turn on.
As demonstrated in the video, the team was able to successfully design and construct a temperature and sensing control system. In the table on the right, you can see the original testing results and what they mean. If the team had access to the proper resources, the LEDs would have been replaced with a relay, which we identified as part of our project objectives, and a heating lamp. But, unfortunately, COVID-19 restricted our access to campus and we were labs. Another loss to the project due to these drastic changes was the remote notification system. While we did identify a Wi-Fi shield that would allow the Arduino Uno to connect to a Wi-Fi network, we were not able to obtain all the necessary supplies to complete the physical addition to the device. Additionally, due to limitations of the available modeling softwares, we could not properly model the use of the Wi-Fi module. The basic circuit schematic for the Wi-Fi enabled device is available in the team's final report, but we did not create an Arduino sketch as we were unable to model or test the remote notification system. All in all, this project was quite successful. The team was able to complete all the project objectives except for one, the remote notification sketch. This would be an area for future research and consideration. This automatic temperature sensing and control system can help relieve stress on leopard gecko owners and keep leopard geckos safe, happy, and healthy. This device could also be expanded in future research to be able to work with other reptiles by editing the temperature threshold data as needed in the Arduino sketch. This device is a helping hand for those extra busy days, but is not a replacement for proper pet care. All pet owners should spend adequate time with their pets, leopard geckos or otherwise.